So the next talk will be given by Chirag, and he will tell us about optimal algorithm for stochastic vertex cover. And he made the mistake of not listing his co-authors on the title slide, so I hope he will later on. So the floor is yours.
Yeah, no, I'll have it on the next slide. Thank you, everyone, for showing up. I'll be talking about our recent work. Sorry. Okay. Yeah, thanks for that. I'll be talking about our recent work on the stochastic vertex cover problem. And this is joint work with a wonderful set of collaborators. That's Jan Vandenbrand from Georgia Tech, Inga Lee Gertz from TU Denmark, Devmalya Panigrahi from Duke, Cliff Stein from Columbia, Miltos and Ola from EPFL, and Ali Vakilian from Virginia Tech. Okay, so let me start by setting up the problem. So in the stochastic vertex cover problem, which was introduced by Benazad, Blum, and Dirakshan, the inputs to the algorithm is an undirected base graph G and a sampling probability P. So that's the input to the algorithm. And then we look at every edge in the graph and independently uh, choose to retain that edge in a realized graph with probability P. So you go to every edge in the graph and sample it independently with probability P. That realizes this graph G star. Um, Importantly, this realized graph G star is not known directly to the algorithm, and the algorithm only has query access to this graph G star. So the algorithm can choose any edge in the base graph G and ask if that edge was realized in the realization. Um, and the goal of the algorithm, after asking a lot of questions like these, is to output a small vertex cover for the realized graph with as few queries it can ask as possible. And just to make sure that we're all on the same page, a vertex cover is a subset of the vertices such that every edge in the realized graph is incident to at least one vertex in the vertex cover, in whatever we output. So in this realization of the graph, those two green vertices constitute a vertex cover because they cover every edge in the realization. So that's the stochastic vertex cover problem. And with respect to some motivation for why we might want to study such stochastic graph problems, you might imagine that in some real world massive graph, right, there are a lot of edges in the graph that on paper we might be knowing of, but there's some inherent uncertainty in whether the edge actually exists in the graph. And an example is this like matching problem in kidney exchange, where we might have a lot of compatible patient donor pairs, which are medically compatible for the kidney exchange to happen. But in order for the exchange to actually go through, one must actually perform many medical tests so that the patients are actually compatible. And if we want to maximize the number of patient donor exchanges that we want to do, we want to solve this stochastic matching problem over maximum matching problem over a realization of the underlying graph. And in fact, this stochastic matching problem has been extensively studied in the literature, and we essentially know the optimal bounds for this problem. Um, and the natural dual problem for the stochastic maximum matching problem is the stochastic vertex cover problem, and that's the problem that we're studying in this. Okay, let me come back to the formalization of the problem. I'm going to denote the minimum vertex cover of the realization by MVC of G star. And what's the benchmark for our algorithm? So the algorithm is going to achieve an approximation factor C if the set that, okay, so the set that it outputs must always be a vertex cover of the realized graph. So you can never output something that misses out on any edge in the graph. So that's a contract. But subject to that, you want to output something that is as, yeah, is the least suboptimal compared to the expected value of the smallest vertex cover of the realization. So the guarantee there is stating that the size that you output in expectation is at most C times the expected value of the realization. And one important point here is that we'll typically only be concerned with the number of queries that we'll make by the algorithm. So we won't be caring too much about the computational power because the minimum vertex cover problem is NP hard. And yeah, we're only worried about how many queries do we need to make to the underlying graph to solve this problem. So we can assume that we can even solve vertex cover optimally for any given graph that we care about, and it's only the queries that we'll be asking about. Okay. So just to get some intuition about what kinds of approximation factors we can achieve via simple methods. So given that the realization G star is actually a subset of the base graph, one simple algorithm is you just output a a minimum vertex cover for the base graph, and that is guaranteed to always be a vertex cover of the realization. But how suboptimal can this naive algorithm be? Well, if you just consider a perfect matching on n vertices, so that's n over 2 vertices on the left, n over 2 vertices on the right. A minimum vertex cover is just you choose one vertex on the left for all the edges. So that's a minimum vertex cover for the base graph. But if you sample every edge independently with probability p, only a p fraction of the edges in expectation are going to be realized in the realization. So if you, the minimum vertex cover in the realization is actually a p times smaller than what this naive algorithm is outputting. So at least this naive algorithm, which makes 0 queries, is not going to achieve a approximation factor which is independent of the sampling probability p. And that is what we want. We want a constant factor approximation problem. And in fact, it has been established that in the original work of Ben Azad-Blum and Dirakshan, that to get any constant factor approximation for this problem, you need to at least query n over p times to the base graph. So yeah, you need to at least do a linear number of queries in the vertices and inverse linear number of queries in the sampling probability. And since then, okay, and in the same paper, the authors also gave an algorithm which achieves a 2 plus epsilon approximation for the minimum vertex cover. Um, and it uses a number of queries which is polynomial in epsilon, but it's also linear in n and p, which is the gold standard given the lower bound. And I must say that this algorithm actually was also efficient, so that's one nice property about the algorithm. Okay, but since then, the 2 plus epsilon factor was improved in this follow-up work by Dirakshan, Durvasula, and Akhtalab to a 1.5 plus epsilon factor. This cannot be efficient, but nevertheless, it uses only n over epsilon p many queries. So that's an improvement over the 2 plus epsilon with a fewer number of queries as well. And thereafter, there was a different algorithm given just last year by Dirakshan, Sanian, and Shun, which actually got the 1 plus epsilon approximation. But the number of queries that it uses is super linear in the number of vertices. So the number of queries it uses depends on this quantity known as the Rusa-Semiradi number of the graph. The definition is not too important, but most important, what's important is that that quantity is super linear in n. So it's still not achieving this gold standard for this problem, which is to obtain a 1 plus epsilon approximation with a number of queries that is order n over p, and some polynomial factors in epsilon. So that's the gold standard which was missing before our work. And so in this work, we give a 1 plus epsilon factor approximation for this problem. The number of queries we use is order n over p times 1 over epsilon to the 5. So up to the dependence on epsilon, this number of queries is optimal given the lower bound by Ben Azad, Blum, and Dirakshan. So yeah, so this is the central problem we resolve in this work. And I'm going to try to, the algorithm that we have is very simple and it's almost canonical for this problem. So I just want to tell you the algorithm. Okay, so what do we do? So we have access to this base graph G. And what we're going to try to do is find a subset of vertices which which we're going to output. And then given that we're going to output that subset of vertices and the contract that whatever we output must be a vertex cover of the realization, we must make sure that whatever we do not output, we must query everything over there and then output a vertex cover for that part. Only then are we going to satisfy the contract that we are always outputting a minimum vertex cover for the realization. So let's just encapsulate this objective into an optimization problem. So what we try to solve is, let's try to find a subset of vertices in the original graph such that if I choose to output this in my vertex cover, in the rest of the graph, what is a subset that minimizes the expected size of the vertex cover over there? So that's the objective that I try to minimize. And I'm going to query everything in the rest of the graph. And my query budget, I want to maintain it to be n over p. So that's the constraint. So in the rest of the graph that I'm going to query, I should have only a few edges, and then I'm going to minimize this objective. So that's kind of a canonical objective that we solve for this problem. And yeah, given this description of the optimization problem, the algorithm basically finds the solution to this optimization problem. Whatever is the rest of the graph, it queries everything over there. That's guaranteed to have only n over p many edges. And then the algorithm finds a minimum vertex cover for that part of the graph, given it knows its realization. And then it just outputs the union of the optimizer and the vertex cover in the rest of the graph. So this is the entire algorithm. It's trying to find this kind of nice core subset of the vertices, which is very likely to be in the vertex cover, subject to the rest of the graph being sparse. Um, and yeah, it's almost in some sense canonical for the contract that the algorithm has to satisfy. The devil is in the analysis of this algorithm, and it gets quite technical, but I'm not going to be able to say anything intelligent about the analysis, but let me just try to say one sentence, which is kind of an advertisement. Um, sorry. So yeah, so to solve this optimization problem, we show that there is a specific subset of the vertex of the graph, um, which itself contains this very nice core subset of vertices, which is likely to kind of give you a lot of information about what should really be output in the vertex cover as a function of the base graph. And like yeah, it's an iterative process by which we build this core subset of vertices. The iterative algorithm tracks a very cute potential function, and yeah, it builds this subset of vertices, and we show that there is a specific p which, when it contains this subset, it satisfies this 1 plus epsilon factor approximation problem. Yeah. Yeah, I really encourage you guys to look at the paper or chat with me afterwards if you want to know more about this. But yeah, given the time, let me summarize what we did in this work. We studied the stochastic vertex cover problem. Goal is to output a minimum vertex cover of a stochastically realized graph. The gold standard for this problem prior to our work was to obtain a 1 plus epsilon factor approximation using only n over p many queries. And we solved this problem. And yeah, I told you one of the key ideas in the paper of finding this like nice core subset of vertices, but we also give a self-contained concentration bound for the minimum vertex cover of a graph that's realized in this manner. So we show how the size of the minimum vertex cover of a stochastically realized graph concentrates around its expectation. And there's some nice martingale arguments that go in showing this property. And yeah, and then there's this nice iterative procedure to build a core subset. Um, and then, yeah, so this problem is resolved in terms of the dependence on n and p. But what's still open is what is the tight dependence on the approximation factor epsilon. Um, and yeah, it seems like, at least via our techniques, there is some slack. Maybe the right dependence, at least through our technique, should be something like n over p epsilon squared. I don't know if we can do anything better, at least in using our techniques, but even so, there's still some gap there to be. But yeah, that's all I wanted to say. Thank you so much.
We have time for a couple of questions. Yes.
I guess two questions. What is the concentration bound? Is it sort of multiplicative or additive, like which follows from McDermott's inequality?
Yeah, so the random variable minus expectation larger than random variable being beyond 1 plus minus epsilon times the expectation is e to the minus epsilon squared times the opt of this problem. So getting something that's e to the minus epsilon squared times n was known before. for our purposes, we needed it to be not n, but opt of this problem. That's something that we,
Yes, so it's multiplicative in that sense. Yeah.
yeah, but in terms of opt somehow.
Okay. And second, I guess, is so what is special about the vertex cover that you're using in your algorithm or analysis rather than, say, some other, say, property or object in that you're looking for? So I'm trying to see, did you use something very
Stick to vertex cover.
vertex cover somewhere, or like it's a more general framework that you could use for, I don't know, related problems? Like, say, if I have vertex cover in some constant degree hypergraph or something.
So maybe two points at least immediately that come to me. So for vertex cover, at least in our constellation bound, because we use this martingale analysis, you can use this stepwise vertex exposure martingale, which you can use. Like if I tell you I vertices, if I tell you what the I realized vertices are, and then I tell you what the I plus 1th vertex is, then there's a bounded change in what this random variable can be. So that's useful in this Doob martingale that we use. And the second thing is maybe, so in this iterative procedure that we use, what's special about the vertex cover is that if in the base graph, there is a vertex that's adjacent to a lot of edges, and this vertex is not included in a canonical minimum vertex cover for the graph, then I need to include a lot of the neighbors in my solution, because there's a lot of edges and most of them are going to be realized. Because this vertex is not in the vertex cover, I should include all of those. So somehow that's a very vertex cover property. But yeah, maybe that.
So while the next speaker shuts up, if there is one more question, you can quickly answer it.
I actually had two, but feel free to answer whichever you want to. One was, you said you don't care about computational time, but what is the computational time for computing this P star set?
Like, yeah, it's impossible. Like, so first of all, you need to, like in the objective function, you need to find the minimum vertex cover of this V minus P for every P. So P is a subset of the vertices, that's 2 to the n many. Now, once you fix one of these, you need to find the minimum vertex cover in the rest. So that's also an impossible problem. So like this really is using a lot of computational power, like definitely like a lot of exponential.
At least single exponential. Yeah.
Yeah,
Thank
yeah.
you. Thanks again.